We will continue our study of capacitance by looking at energy of a charged capacitor. Well, obviously, when a capacitor is charged, it contains energy. It is capable of doing work. A charged capacitor can light up a bulb, can drive a motor. Is that right? It can do many different kinds of work. It can do work because it acquires energy while being charged. So, the question we are trying to answer is, what is the energy stored in a capacitor? In order to charge a capacitor, work needs to be done. How is work done? We need to transport charges and put them on the capacitor plates, and that needs energy. So charging a capacitor, you need to spend energy. That means you store energy in the capacitor. Work done in charging a capacitor is stored in it as energy. Now, let Q be the amount of charge on the capacitor of capacitance C. So, let us say, to begin with, the capacitor plate has an amount of charge Q and its capacitance is C. Now, remember, capacitance is a constant. Now, the amount of charge Q raises the potential of this conductor. I have just taken one capacitor plate. The amount of charge Q raises the potential of the capacitor plates to V. Now, what is the definition of potential? Potential is defined in terms of work done, isn't it? Potential is joules per coulomb. How much work needs to be done to move 1 coulomb of charge? Now, its potential is V, means if you now want to move 1 coulomb of charge and put it here, you need to do V joules of work. That is the meaning. So, as the potential of the conductor increases, the work you need to bring in more charges to the capacitor also increases. So, if Q is the amount of charge on a capacitor plate of capacitance C, then the potential of the conductor will be V equal to Q over C. Now, if you want to now transfer an additional charge dQ, remember this V stands for what? Work done per unit charge. If I want to move 1 coulomb of charge now and put it on this capacitor, I need to do this many joules of work. Now, if I want to move an amount of charge dQ, the amount of work done will be then V times dQ. So, dW, the amount of work done to move a charge dQ, will be dW equal to V dQ. That means if I want to move this small amount of charge dQ, I need to do an amount of work dW equal to V dQ. That means each time I move a charge dQ, it raises the potential. That means next time I want to move another dQ, I need to do a little more work. So, as the potential of the capacitor increases, in order to bring the next batch of charge, I need to do more work. So, in order to find the total work, in order to transfer a total amount of charge Q to a capacitor, the amount of work can be obtained by integrating dW. Is that right? So, integrating dW from, say, V1 to V2, the potential increases from V1 to V2. And we can show that it is equal to 1/2 CV squared. Well, I think you need to do that. Let's see if we can do that. So, to move a small amount of charge dQ, the amount of work done is V dQ. And so, if you want to find the total work done when the amount of charge increases from an amount Q1 to an amount Q2, all we need to do is integrate this dW from Q1 to Q2. Now let me do that on the whiteboard. Now watch these steps. The total amount of work done when the amount of charge increases from Q1 to Q2 will be integral Q1 to Q2 dW, and that will be integral Q1 to Q2 of dW is V dQ. Now, in order to work out this integral, you know that V is a variable, Q is a variable. Now you cannot have two variables when you want to integrate. So what we need to do is replace this V in terms of Q, because we are going to integrate with respect to Q. Can you give me a quantity which I can replace V by? Well, you know capacitance C equal to Q over V. Therefore, V can be written as Q over C. Is that right? Yes, let's do that. Well, you know that C equal to Q over V. That means V will be written as Q over C. So that will be integral Q1 to Q2. We will replace V by Q over C dQ. And 1 over C is a constant. Integral of Q1 to Q2. Now, Q dQ can be now written as, I'm going to disregard the limits. We will do the integral without the limits. So that will be 1 over C. What is integral of Q dQ? Integral of Q dQ will be Q squared over 2. So the work done will be 1 over C times Q squared over 2, which I can write as 1/2 of Q squared over C. Alright, so this is one expression for work done in charging a capacitor. And remember, work done in charging a capacitor is a measure of the energy of the capacitor. So what is an equation for energy of a charged capacitor? Energy of a charged capacitor is Q squared over 2C. Q squared over 2C. Can you show that this is the same as 1/2 CV squared? Well, that's not difficult, because Q equal to CV. Q squared is C squared V squared divided by 2C, and 1C will cancel, and that is 1/2 CV squared. So the energy of a charged capacitor is Q squared over 2C, that is one form, which is the same as 1/2 CV squared. So in the first one, it contains Q and C. The second one is in terms of C and V. So you must be familiar with these forms. The energy of a charged capacitor is Q squared over 2C, which is the same as 1/2 CV squared. So if a capacitor is charged to a voltage V, then the energy stored in the capacitor is E equal to 1/2 CV squared, which is the same as Q squared over 2C. Okay, let's do a problem. Half the charge is removed from a capacitor without changing its capacitance. What fraction of its stored energy is removed along with the charge? Well, when you remove charges from the capacitor, from the charged capacitor, you are removing energy from it. So half the charge is removed from a capacitor without changing its capacitance. Well, of course, removing the charge will not change the capacitance. What are we supposed to find? Find the fraction of the stored energy that is removed along with the charge. Alright, let's consider a capacitor of capacitance C carrying a charge Q. What is the energy E1 of that capacitor? E1 equal to Q squared over 2C. And now what is done? Half of this charge is removed. So what is remaining in the capacitor is only half of this. The capacitance C of a capacitor is a constant. That doesn't change. Now, it doesn't depend on the amount of charge on it. You know that. When half the charge is removed, the remaining charge is Q over 2. Therefore, can you write an expression for the energy of the capacitor after half the charge has been removed? If E2 is the energy after removing half the charge, then E2 will be, look at this, energy will be Q squared over 2C. Now this time, only half of the original charge is now remaining. So Q over 2 is the remaining charge in the capacitor. Square that and divide it by 2C. The capacitance doesn't change. And what does that become? That will be Q squared over 8C. I'm sure you can understand that. This will be Q squared over 4, and that 4 will go to the denominator to get that 8C. Now, what was the energy originally before the charge is removed? It was Q squared over 2C. After half the charge is removed, the energy of the capacitor is Q squared over 8C. So what is the amount of charge that is removed? Well, the amount of charge that is removed is Q over 2. Well, let me write it like this. It will be 1/4 of Q squared over 2C. Q squared over 8C is 1/4 of Q squared over 2C. Why did I write like that? Because Q squared over 2C is the original energy before the charge is removed, which is E1. And so, E2 equal to 1/4 of E1. That means when half the amount of charge is removed from the capacitor, the energy of the capacitor now is only 1/4 of the original energy. Therefore, the energy removed, how much energy then got removed, is initial energy minus the final energy, E1 minus E2. What is that? E1 minus E2. E2 is 1/4 of E1. That is 3/4 of E1 is actually removed. What fraction of its stored energy is removed? 3/4 of the original energy has been removed by taking away half the charge. I hope you understand the problem. Okay.